All right, today we are going to look at section 2 of chapter 2, which is on set operators. You can also refer to those as set operations, so operations performed on sets. We have 6 vocabulary terms today. One of them is union, intersection, complement, disjoint, difference, and cross product. 5 of 6 of these terms are actual operations, and one of them is just a relationship between two sets. Let's go ahead and point out which one that is. This one right here, this is not an operation. Disjoint is actually going to be a relationship. If I can get this thing to work here. There we go. So our first term here is union. The definition is let A and B be sets. The union of A and B, written A union B, is the set of all elements that belong to either A or B or both of the sets. So if we were to look at an example here, let's consider the sets L and K, and we wanted to talk about their union. So what would their union be? Well, it would be the set of 1, the set of 2, the set of 3, the set of 4, the set of 5, the set of 6, the set of 7, the set of 8, the set of 9, and the set of 10. That would represent the union of sets L and K. That is any element that's in either one of them or both. So you basically put them all together. Our next definition is intersection. Let A and B be sets. The intersection of A and B, written A intersect B, and that kind of got chopped off there a little bit, so let me see if I can write that up here. So A intersect B, kind of got this chopped off down here a little bit, is the set of all elements that belong to A and B. So let's look at the two sets P and Q. P is the set of perfect squares. Looks like I got 1, 4, 9, 16, and 25. Those are perfect squares. And then Q is the set of 1, 2, 4, 8, 16, 32, 64. I wonder what numbers those are. So what would be P intersect Q? What would be the intersection of these two sets? Okay, so it has to be the things that are in both of those. So let's see here. What would be in both of those? I'm trying to do some set notation here, but it's not letting me do it. There we go. So let's see here. Is 1 in both of them? Yes. Is 2 in both of them? No. 4 is in both of them. Is 8 in both? No. Let's see here. 16 is in both of those. And that appears to be it. So the intersection of sets P and Q would be the set of 1, 4, and 16. Those are the elements that are in both of the sets, A and B. Complement. Given a set A, the complement of A is the set of all elements in the universal set, but not in A, symbolically written as A complement. So, if we look at our example here, we have the universal set, which is the set of everything in this particular problem, is 1 through 6. Set A is 1, 3, 4, and 6, and set B is 2, 4, and 6. So then A complement would be the set of things that are in the universal set that are not in A. So for example, 2 is in the universal set, but it is not in A. Let's see here. It looks like 5 would be the other number that would be in the set of A complement. B complement is going to be the set of things that are not in B. So let's see here, but are in the universal set. So 1 is in the universal set but not in B. 2 is in B, and so we can't get rid of that one. 3 is in the universal set but not in B. 4 is in B. 5 is in the universal set and not in B. So the complement of B is the set of 1, 3, and 5. All right, disjoint. If two sets A and B have no elements in common, That is, A intersect B is the empty set. Remember, our definition for intersect means the things they have in common. So A intersect B means the things they have in common is the set of nothing, or in other words, there is nothing that they have in common. We call them disjoint. Now down here I've got a graphic here with a set of A, which looks like we've got a pentagon and looks like a rhombus here, and then a trapezoid. And then down here in set B we've got like a rectangle, a square, equilateral triangle, and a star shape here. Do these two sets have any shapes in common? And the answer is no, they don't. So they would be called disjoint. Let's look at a numeric example. So let's say that we have the sets G and F. Set G is, well, it looks like even numbers, 2 through 10. Set F has the odd numbers, 1 through 15. These two sets are said to be disjoint since they have no common elements. Difference. So you probably remember back when you were in school, in elementary school even, you talked about subtracting or the difference of things. So 6 minus 4 is 2. So if you had 6 pebbles together and you took away 2, then you would still have, if you had 6 pebbles and you took away 4 of them, then 2 of them would be remaining. It's a similar thing here with set theory. If you have two sets A and B, the difference, written just like you would in arithmetic, A minus B, is all of the elements that are in A but not in B. In other words, you remove the things in A that are in B. This is also referred to as the relative complement. So let's look at an example of this. Oh, here it is symbolically. This is the set builder notation for it. So it would be all the values of x such that x is an element of A and x is not an element of B. So here's some examples. Let's consider the set M, which is the set of 1 through 10, and the set N, which is the set of 1, 2, 4, 8, 16, 32, and 64. Let's find M minus N. So that means this set is going to be built of the values of x such that x is an element of M and x is not an element of N. So, is 1 an element of is 1 an element of M and not an element of N? Well, no, so it does not go in part of our answer. What about 2? Is 2 an element of M and not an element of N? Well, nope, that doesn't work either. However, let's look at 3. Is 3 an element of M? Oh yeah. Is 3 not an element of N? Yeah, that is correct. So we are going to put 3 in here. Alright, what about 4? Well, 4 is an element of M, but it is also an element of N, so that doesn't go in our set. 5, let's see here, 5 is an element of M and is not an element of N, so 5 goes in here. 6 also goes in here. 7 goes in here. 8 does not. 9 goes in here. And then, of course, 10 is going to go in there because, again, 10 is an element of M and 10 is not an element of N. So M minus N will be 3, 5, 6, 7, 9, and 10. Cross product. This is our last operation. Given two sets A and B, their cross product, denoted A cross B, is the set of all ordered pair combinations that form sets A and B. They're from sets A and B. Also referred to as the Cartesian product. So symbolically, if we're doing a cross product, typically we do it of two sets, we're going to build ordered pairs with that. It's kind of best to see an example of it. And by the way, this is different than the cross product you might be used to in Algebra 1. So let's see an example. Let's say that I have the set R, which is 5, 10, and 15, and then the set S, which is the set of 1, 2, and 3. So the set R cross product S is going to be equal to the ordered pairs of R and then S, and we have to do all the different combinations. So we would have 5 from the first set, you could have 1 from the second, you could have 5 from the first set with 2 from the second, you could have 5 from the first set and 3 from the second, you could also have 10 from the first set and 1 from the second, you could also have 10 and 2 and 10 and 3. I'm really sorry about my poor handwriting. And then we could have 15 and 1. We could have 15 and 2. And then we would have 15 and 3. Notice that the order is important here, and I need some parentheses in there. The order is important. Since this is R cross S, I had to put the ordered pair for R in the front, so that's why the 5s are in the front, the 10s are in the front, and the 15s are in the front. And then the S came second, so those go with the second. And you'll notice that there are 9 total pairs here, cross product. Okay, so now I've done some examples. I want you to try to do some on your own. Here are the sets that we're going to use, so you might want to jot these down on a piece of paper. You might want to pause the video. There are our universal sets, our universal set, the set O, which is the odd numbers, the set E, which is the even numbers, the set P, which is perfect squares within that set, that universal set. So I'm going to have you do some problems now, but I want to let you know that the answers for these next questions are going to be, I'm going to attach those to my big campus, and I'm just going to go ahead and attach them to my webpage too, just in case. And I would recommend that you don't look at the answers until you've attempted all the problems. So, set 1, I want you to find the following. You're going to do E complement, you're going to do E intersect P, and then you're going to do O union E. So if you want to pause the video and go ahead and do that now, you can, or you can go ahead and go to the next slide. Oh, I'm sorry, I have one more here. So number 4 here is O intersect parentheses E complement union P. So here you need to do your order of operations. This one's not too difficult, but you do need to follow the order of operations. So you're going to have to do E complement first, then the union, and then the intersection. Problem set 2. So here's what I'd like you to do for those. You're going to do E cross product P. You're going to do O minus P. And then you're going to do O cross product parenthesis E minus P complement. So again, you have to deal with some order of operations here before you do your cross product. These answers will be attached to my webpage and my big campus. Here's a proof, and I'm not going to offer the proof yet. I'll let you ponder it. But suppose I make the statement that A intersect B, that intersection complement is equal to A complement union B complement. How would you show that this statement is true? How would you show it? In other words, how would you prove it? And you could do that in a verbal explanation, or you could even do it symbolically. This is kind of a higher level thinking problem. See if you can figure that out. And then finally, story problem. Suppose there's 20 students at school. Some swim, some participate in the math league, some do both. We know that there are 13 swimmers and 12 are in the math league. How many students do both? Now I have this answer also as part of the answer sheet that's attached to the website and my big campus. So I think that wraps this one up. So hopefully you've done those problem sets 1 and 2, and then check your answers.